Hello and welcome back to Counting Rocks and Introduction to Combinatorics at CSU. Today we're going to be talking about linear recurrences. In the last video we started recurrences in general, and now we'll look at a special type that we can always solve. So here are some examples of linear recurrences. A sub n equals a sub n minus 1 plus a sub n minus 2. The Fibonacci recurrence is linear. Or b sub n equals 2b sub n minus 1 minus b sub n minus 3. Or c sub n equals c sub n minus 1 minus c sub n minus 2 plus 5c sub n minus 3. What do all these have in common? They have the common form where the nth term is some linear combination of the previous d terms. This is called a depth d recurrence, where you have coefficients c1, c2 up to cd on an minus 1, an minus 2 up to an minus d, and you add them all up. So these three have depths 2, 3, and 3. Here's some nonlinear recurrences. What isn't a linear recurrence? If you go all the way back to 0, that doesn't have a constant depth. The depth keeps getting bigger as n gets bigger. So this would not be considered a linear recurrence, even though it looks like one. And if you have a times, so e sub n equals e sub n minus 1 times e sub n minus 2, that's certainly not linear. Or if you have like sine of e sub n minus 1 or some other function of it that's not a linear combination, anything else is not a linear recurrence. So let's just look at the linear ones today. So let's first take a look at a combinatorial problem that can be easily solved by finding a linear recurrence. How many ways can you climb a staircase with 8 steps using steps of sizes 1 or 3 at each step? Let's let s sub n be the number of ways for n steps in general. We'll look for 8 steps in the end, but let's just solve it in general as a recursion. The first step can either be size 1 or size 3. If you go up 1 step, there's n minus 1 steps left. If you go up 3 steps, there's n minus 3 steps left. So the number of ways to get to the top of a staircase of size n with this funny way of walking is s sub n minus 1 plus s sub n minus 3. So there's a linear recurrence, and of course, like we did with Fibonacci numbers, we can just write them out. We can figure out the initial conditions that there's one way to climb no steps, you're already done. There's one way to climb 1 step because you take 1 step of size 1, and there's only one way to climb 2 steps because you can't skip 2, you can only do 1 and 1. And then there's 2 ways to do 3 because you can take the step of size 3 or 1, 1, and 1. So we know our initial conditions, and then each number is the sum of the one before it and the one 3 steps back. And so we can unwind this recursion and find that for 8 steps, there are 13 ways to do it. So our goal here is to find an explicit formula for all linear recurrences, but let's start with depth 1 linear recurrences, which are the simplest to solve. Let's say we wanted to find an explicit formula for the recursive sequence defined by a sub 0 equals 5 and a sub n equals 3 a sub n minus 1 for all n at least 1. So we start at 5, then we multiply by 3, then we multiply by 3 again, then we multiply by 3 again, and actually by leaving it unsimplified, you can easily see what the formula is in all cases. It's going to be 5 times the power of 3. So we guess the explicit formula a sub n equals 5 times 3 to the n, and you can check that that satisfies the recursion and the initial conditions. And in general, for depth 1 recursions, this is always going to happen. If a sub 0 equals m is your initial condition, and a sub n equals r times a sub n minus 1, then it's going to be m times r to the n for the nth step. Depth 2 is a lot more interesting. Let's now find an explicit formula for the depth 2 recursion defined by the initial conditions a0 equals 2, a1 equals 5, and a sub n equals 5 a sub n minus 1 minus 6 a sub n minus 2. So by playing around a bit, you might guess that, well, maybe the powers of something would satisfy this recursion just like they did for depth 1, and you'll find that 2 to the n and 3 to the n actually both satisfy this recursion. We can plug them into the right-hand side. 5 times 2 to the n minus 1 minus 6 times 2 to the n minus 2. You get 6 is 2 times 3, so you can put one of the 2's in with that 2 to the n minus 2 to make another 2 to the n minus 1. Factor out the 5 minus 3, and you get 2 to the n. So 2 to the n satisfies it. A similar computation shows that 3 to the n satisfies the recursion. And we only need the initial conditions to be satisfied now. And the cool thing about a linear recursion is once you have 2 solutions, then any linear combination of those 2 solutions is going to satisfy the recursion as well. So then you just need to find a linear combination that satisfies the initial conditions. And if you add 2 to the n and 3 to the n, well then for n equals 0, we get 1 plus 1, which is 2. And for n equals 1, we get 2 plus 3, which is 5. So that satisfies the initial conditions. So our answer is a sub n equals 2 to the n plus 3 to the n. But how would we have thought of that? What if it's not easy to guess the powers, something to the n and something else to the n, that satisfies this recursion? This is where a special polynomial comes in called the characteristic polynomial of the recursion. 2 and 3 are the roots of x squared minus 5x plus 6. If you factor this, it factors as x minus 2 times x minus 3. This looks a lot like this recursion in the sense that it has 5 and 6 showing up in the coefficients. In general, the characteristic polynomial of a linear recursion of the form a sub n equals b a sub n minus 1 plus c a sub n minus 2 is x squared minus bx minus c. Why do we change this b and c to minus b and minus c? Because I think of actually moving these two terms to the other side of the equation to make it all on one side equal to 0. And then you're looking for roots of that equation. And so the characteristic polynomial is x squared minus bx minus c if you write the recursion this way. So here's the characteristic polynomial, and our lemma is that if r is a root of the characteristic polynomial, meaning it satisfies this equation, then r to the n is a function that satisfies the recursion. It might not satisfy the initial conditions you're looking for, but at least it is a solution for the recursion itself. And the proof is really just plugging into the recursion. So if we plug it in to the modified version of the recursion where, like I said, we put everything on one side of the equation and it's set it equal to 0, then plug in r to the n here and r to the n minus 1 and r to the n minus 2, and we get this expression, which we can factor out r to the n minus 2 out of, and we get r squared minus br minus c. And r squared minus br minus c is exactly this side with r plugged in for x, which we know is equal to 0 because r is a root. And so this whole thing is indeed equal to 0. So let's talk now about how to solve depth 2 linear recurrences in general. Say we have initial conditions a0 equals I and a1 equals j, and you have your recursion that's linear of depth 2. Let's consider the characteristic polynomial and say it has distinct roots first. There's actually a separate case where it has equal roots. But if you have different roots, r1 and r2, like we had with 2 and 3, then r1 to the n and r2 to the n satisfy the recursion. And so a general formula for something that satisfies the recursion is s times r1 to the n plus t times r2 to the n for some s and t. And finally, you can solve for s and t using the initial conditions. Plug in n equals 0, plug in n equals 1, and you'll get two equations in two variables s and t. You solve, and that gives you your unique solution to that depth 2 linear recurrence. Now, what about that pesky case where there's a double root, where it factors as x minus r squared? So you don't have two different r1 to the n and r2 to the n. Well, now what are you going to do with an s and t? You need two variables. Well, it turns out when there's a double root, you can do a little more algebra and show that n times r to the n also satisfies the recursion in that case. And so the general formula is actually s times r to the n plus t times n times r to the n, and that will be what your explicit formula looks like for some s and t. Again, you solve for s and t using the initial conditions. Nothing different at that step. Let's do an example of this tricky case where we have a double root. Say this is our recursion with a0 equals 3 and a1 equals 8. The characteristic polynomial is now x squared minus 4x plus 4, which factors as x minus 2 quantity squared. And so a sub n is s times 2 to the n plus tn 2 to the n for some s and t. To find s and t, we plug in 0, and so plugging in n equals 0 here makes this whole term go away, and this term is just 1, so a0 is just s, and we also know a0 is 3. So s equals 3. For a1, then you plug in n equals 1, you get 2s plus 2t, and we know that has to equal 8 by the initial condition. And so you plug in s equals 3, you solve for t, you get t equals 1, and so we conclude that a sub n is 3 times 2 to the n plus n times 2 to the n for all n. Now let's look at the general case of depth d. A sub n equals c1 an minus 1 plus c2 an minus 2 plus up to cd an minus d, not just depth 2 now. Now the characteristic polynomial is constructed in the same way, x to the d minus the rest of the coefficients times the smaller powers of x. And this characteristic polynomial may have many roots. Some of them may be equal to each other, so many of them may be different from each other. And so we say if r is a root with multiplicity m, that means r occurs m times. X minus r to the mth power is the biggest power that divides f of x. Then you can show that r to the n times r to the n squared times r to the n, up to n to the n minus 1 r to the n, are all things that satisfy the recursion. And so you take a linear combination of all of those for each root. So you have a lot of s's and t's. And so a sub n is a linear combination of all these, and it's determined by the initial conditions. You get a big linear equation, you solve for the coefficients, and in principle, you can solve every linear recurrence explicitly with this algorithm. So let's go back to our counting problem and see how we could have done it explicitly instead of recursively. We can start with our recursion and then find an explicit formula for the number of ways of counting the steps. Or as explicit as we can, because this is a depth 3 recursion, so we have a cubic equation, which is hard to solve algebraically. Fortunately, we can use Sage to solve it approximately. I've put some of the approximate values here, but Sage can do it out to many more decimal places. And you can approximate the roots of the characteristic polynomial, make a linear combination of them, solve for q, s, and t here as the coefficients, and then plug in, finally, when you get a formula for a sub n, plug in n equals 8, and it'll say that it's approximately 13. So I did this on Sage, and here's what it looks like. You code your polynomial, you find your roots, r1, r2, r3, you try to solve for the coefficients, q, s, and t, and then finally we get an equation that we plug in 8 for, and you get 13.00000. I think that's pretty close to 13. So this is amazing because we're using numerical approximations to get an integer, but we know since it has to be an integer in the end, even if it had like a little 1 out here because of some floating point error in the computer, we would know that the answer is 13. So now you try. Find an explicit formula for the recursively defined sequence a sub 0 equals 2, a sub 1 equals 1, and for all n at least 2, a sub n equals a sub n minus 1 plus 2 a sub n minus 2. That's all for today, and I'll see you next time.